Assalamualaikum and a very good morning. So today I will be presenting about my research titled 3D printed micropump fabrication and characterization. This will be the outline of my whole presentation, which includes the introduction, objectives, methodology, results, and last will be the conclusion. Microfluidic systems have garnered significant interest over the last decade due to their ability to consolidate several laboratory operations onto a single chip, thereby permitting point-of-care testing technology. So there are few applications in biomedical that are using these devices, such as for glucose monitoring, hemostasis, cardiac indicators, drug screening, and pregnancy testing. However, these devices require external bulky power supply for active pumping. Therefore, the self-powered infusion micropump is a novel design solution for a passive pumping mechanism that flow is driven by the capillary actions. Most of the microfluidic device fabrication has been accomplished by using soft lithography that was first introduced by G.M. Whiteside's research group in 1998. So this soft lithography is actually a group of methods that utilize elastrometric stamps for patterning or molding the features geometry, and it can provide many advantages such as a biocompatible, oxygen and carbon dioxide permeable, chemical inертness, versatile chemical structure, and mechanical flexibility, and also durable. Usually, for this soft lithography, SU8 mold is being used as for the master prototype. So this mold is the most common photoresist for master fabrication due to its ability to maintain chemical and thermal stability after UV polymerization. However, this SU8 mold fabrication processes requires expertise and very time consuming, and also it can be expensive. Therefore, 3D printed mold has become an alternative to replace the SU8 molding in microfluidic fabrication, as it requires less expensive equipment and can provide speedy construction of complicated 3D objects. SLA technology in 3D printing is the most popular in microfluidic, as it can produce the high precision, less severe roughness, high resolution, time efficiency, and reliability. So in recent years, SLA application in medical field have been expanding, especially in orthodontic surgery. However, SLA 3D printed part as a mold for soft lithography remain as a challenge for curing inhibition of PDMS for all commercially available resins. So the main objectives of this research is to evaluate the fabrication process of the 3D printed mold, to establish the adaptability of SLA technology in soft lithography, and lastly is to characterize the fabrication quality of the 3D printed mold. This is the flow of the methodology, which consists of the design drawing using AutoCAD, SLA 3D printing of the master mold, evaluation of the properties of SLA 3D printer, characterization of the mold, and the dimensional comparison of 3D printer mold to the SU8 mold. Figure 1 shows the dimension of the micropump design, which has been revised from its initial version by Daldoso in 2018. The mold is been printed using Z-Rapid SLA660 industrial SLA 3D printer, while as for the characterization, it was carried out under an optical microscope through isolation light software. Table 1 shows the mold fabrication process for SU8 and also the 3D printing. So as you can see, additional post-processing may be necessary depending on the surface finish of the mold. And usually it happens for FDM printing mechanism. And the soft lithography with 3D printing technology simplifies the manufacturing a microfluidic device from the conventional SU8 molding, particularly by obviating the need for spin coating, soft baking, UV light exposure, post-exposure baking through a single printing process. So as you can see, the SU8 method is actually more complicated in the final processing steps compared to the FDM and SLA. Next is on the comparison of the mole fabrication in terms of its duration, cost per mole, surface roughness, and also water contact angle. So as you can see from table 2, SU8 mole took the longest time to be done compared to FDM and also SLA. And as for the cost, the SU8 mole is most expensive compared to FDM and SLA. And next is on the surface roughness. SU8 mole can provide an extremely smooth surface finish with 0.04 micrometer. And as for the water contact angle, the FDM is having the highest water contact angle, which is 95 degree. Next is on the SLA 3D printed mold. So the ABS light resin has comparable mechanical properties to ABS thermoplastic. So as you can see from figure 3, there is no significant visible apparent line on the surface feature of the printed part. And from the figure 4, you can see the isometric view of the micropump components. And this device can be accurately printed. All the micropump components, small structures, can be printed according to the design input without any defects, even to the parts that are prone to printing failure, such as the edge of the narrow microchannel and also the circumference of the holes. Figure 5 shows the cured PDMS replica molding fabricated using the 3D printed mold. Next is the results and discussion on the percentage error of the micropump elements. So the degree of variation of the printed mold dimension was analyzed in the form of error percentage on 5 sections, which are the inlet and outlet hole, trapping chamber, working liquid, and sample liquid channels. So the outlet hole has the highest percentage difference between its measured value and the actual design value, with a dimensional error of 94.79%, while the trapping chamber has a percentage error of 87.14%, while the inlet hole has a percentage error of 65.90%. In the contrast, the straight microchannels width of the inlet and also outlet have dimensional of 4.26% and 8.95% respectively. And the overall average percentage error for all 5 sections is 6.61%. This percentage error shows that the SLA printer can create better straight channels compared to the circular cross-sectional area. Next is on the coefficient of variation for micropump elements. So the highest coefficient of variation is at the inlet with 8.25, and the lowest is at the trapping chamber, which is 0.89. So the calculated average coefficient of variation from these 5 sections is 3.22, and this is still acceptable as it is below the standard value of 10. To establish the most appropriate printing mechanism for simple micropump fabrication, the geometrical error of an ABS light mold was compared to the geometrical error of an ABS mold made using FDM 3D printing. So the printed working liquid channel width of ABS mold deviates by 23.38% compared from the designated value, while for ABS light mold has a minor dimensional error of 6.61%. So this results due to the shrinkage of the ABS material throughout the printing process. Lastly, as for the conclusion, 3D printing techniques are economical for prototyping and technologies enhance cost effectiveness and speed. In comparison to SU8 molding, FDM as SLA cut the manufacturing time by 60.87% and 30.43%, and it can cut its cost by 94.39% and 82.84% respectively. So circular cross-sectional area can gives a high dimensional error reaching up to 64.79% compared to the straight inlet and outlet channels with a dimensional error of 4.26% and 8.95% respectively. The inlet hole has the highest CV value of 8.25, while the trapping chamber gives the lowest value of coefficient of variation, which is 0.29. So when comparing 3D printing of molds, it is observed that SLA can generate features with high degree of accuracy, as seen by the slight variation of microchannels from the actual structure, which average 6.61% compared to 23.38% for FDM. That's all from me. Thank you.